Hello everybody. As we talked in the last lesson, we're going to continue with the rate of change, which we define as the slope of a line, or the ratio between the change in dependent variable over the change in dependent variable. In these examples and during this lesson, we're going to see how to figure out the rate of change when we have a table of values or when we have a graph. And in both cases, we're going to use the formula y2 minus y1 over x2 minus x1, which is rise over run. Okay, let's view a few specific examples to illustrate this. On this first example here, we are given a table of values, and we are required to figure out what is the rate of change and explain the rate of change that is represented here. What will it mean in this specific example? All right. So we're going to use, as we said, the formula change in height over change in time. Why change in height over change in time? Because that's what our dependent and independent variables are. Our independent variable is time, and our dependent variable is height of the aeroplane in meters, whereas the time is measured in seconds. As we mentioned, the units are very important to state at the end. Okay, so to figure out the average rate of change, we're going to use the formula change in height over change in time. Use these 2 points to figure out what is the average rate of change. So we're going to have 1400 minus 2000 divided by 4 minus 0, and we end up with the slope of, or average rate of change of, negative 150 meters per minute. What does that mean? It means, since we have a negative slope, it means that the airplane is going down, so the height of the airplane is decreasing by an average rate of change of 150 meters per minute. On the second example, we have a graph, and as you see here, the graph has the title, and both axes are labeled, including the units, so we can easily determine what the graph represents. So it's how much we pay, what is the cost when we rent a vehicle based on the distance that we are driving. Okay, we're going to use the same formula, the change in cost, because that's our dependent variable, divided by the change in distance driven. And the 2 points that are given here, that is what we're going to use to substitute in this formula. And from here, we figure out that we pay $1.50 per each kilometer that we are driving. All right. On the second example now, before we continue the slope, we have to recall a little bit what is the reaction distance, what is the braking distance, and what is the stopping distance. The reaction distance is it starts from the momentum when we think that we need to stop until we hit the brakes. So that is the reaction distance. From the moment that we hit the brakes until we stop, that is the braking distance. Adding these 2 times together create what is called the stopping distance. In these 2 tables down here, we are given the reaction distance and the braking distance with respect to the speed at the specific times, and we are required to figure out what is the average rate of change between consecutive points on each table. And then based on that result, we're going to describe what does that mean, the meaning, what can we read out of that. Let's start first with the first table. So we're going to analyze the speed and reaction distance. How do we figure that out? For each 2 consecutive points, we're going to write or create the ratio change in distance over change in speed. So we're going to start from the second point, 2, and we're going to subtract the y values first, or the dependent variables first. So 2 minus 0 over 10 minus 0. And then we have a ratio of 0.2. We do the same thing with the following two consecutive points. 4 minus 2 divided by 20 minus 10. And then we continue until the end of the table. 6 minus 4 over 30 minus 20. 8 minus 6 over 40 minus 30, and so on. And as you notice here, the ratio is the same for all the consecutive points. What does that mean? That means that the reaction distance increased by 0.2 meters for every kilometer per hour increase in speed. So we see that this is the same number. Keep that in mind. So we have the same number here. On the second table, when we compare the braking distance with respect to the speed on a given time, we see that we approach it the same way. Of course, we do the differences between the two consecutive points, figure out what is the rate of change for each consecutive points, and as you see, we notice here that the rate of change is different for each consecutive points. Okay, the rate of change on its own is increasing, 0.05 in the first set, 0.15 on the second, and so on. Now, let's keep both of these results in mind, and let's compare their graphs. Okay, here we have both graphs. In the first one, we have reaction distance and speed. So as you see here, the graph is represented by a straight line. And if you recall from the table, we ended up having the same rate of change here. We can notice that as well from the graph, rise over run, and as you see, the slope is the same. So we have the graph is represented by a straight line here. And we can conclude that since the rate of change is the same, so here we can write the same, for each 10 kilometers per hour, the point on the graph lie on the straight line. Okay? All right, let's see now what is happening on the second graph. As you see, we have a curve here. And if you compare from the table, we notice that the rate of change is increasing. And we can notice that here from the graph as well. As you see, the distance from one point to another on the speed or on the independent variable are the same. However, the rise is not the same. The rise is increasing for the same distance on the run. So that means that the rate of change is increasing. And as you see, since the rate of change is changing, the points do not lie on the straight line. They are on the curve that is not a straight line, and we're going to see later on what we call this. All right, now we're going to move on to a different example when we're going to apply all this knowledge and calculate it. On this table, we have the growth of a tomato. The time is measured in weeks, and here is the height in centimeters. And we have plotted this data, this table, on this graph, right? And we have calculated the rate of change for consecutive points on this other table. And we are asked to figure out what is the rate of when, or in what weeks, the rate of change is 0, constant, or changing. All right. In order to figure that out, let's use the table first. As you see in the table here, the rate of change is 0, so the third column represents the rate of change, which we also call the first differences. So the first differences the first differences is 0 only on the last row here. 90 minus 90 equal to 0 we have here. And when did we have that value? Between weeks 16 and 18. So let's go back to how that is represented on the graph between week 16 and 18. We have a horizontal line here, which makes sense because we're talking about a slope of 0. So on the table of values, if we talk about rate of change of 0, is obvious. From the graph, we're going to see for horizontal lines. Okay, constant now. We're going to see when we have a constant. Constant means that we're going to have consecutive or the same slope. When do we have the same rate of change? When do we have the same slope from the table? In between what weeks? So we have 5 and 5 here, and that happened from week 0 to week 4. Let's see on the graph. That is represented by a straight line, and as we saw in the previous examples, yes indeed, when we have a constant rate of change, that part of the graph is a straight line. Our next question is, or our next task is to determine where the rate of change is changing. Now let's go back at the table again. We go from on week 6, or from week 4 to week 14, or to week 16 to be more precise. We see that the rate of change, or the first differences, are different. They're changing from one point to another, and that is the period when the rate of change on the growth of the tomato is changing. And how is that represented on the graph? It's a curve. It's not a straight line. It's not a horizontal line. It is a curve that is increasing from week to week. And as we see here, at week 12, the average rate of change has started at week 10. Actually, it has started to slow down until it reaches the constant rate of change. Remember to complete the table where or to differentiate when the rate of change is constant, when is 0, and when is changing, how that will look on the table, and how will that be represented on the graph. All right, hope that was helpful, and I'll see you on Thursday.